This is the last KCS talk for this semester. The speaker for today is Dr. Siddique. Does Siddique? Yeah. That's the right way to pronounce it? Yes. Siddique, all right. He will take you to an area called the World of Language Model. Okay. Dr. Siddique will first take a detailed look of the so-called large language model, or LLMs. All right. He will then delve into the latest development in this area, LLMs. Okay. And then finally, the speaker will take you through some of the work of his students, okay, which are based on pre-trained LLMs. So let's welcome Dr. Siddique. And one more thing. Please sign your name on the sign-in sheet before I enjoy your pizza.
All right. It looks like I'm audible. Okay. Okay, so I will take you through the journey of language modeling. First we'll go to history and then we will keep current. Okay. This is the last keeping current, so we will be current at that. Okay, so let us start with language modeling. What language models are? I believe all of you have some sort of maybe very, very small language model in your pockets. This keyboard, few megabytes, maybe 50 or not more than 100 megabytes of language model. These keyboard suggestions you see whenever you start typing, you start seeing these suggestions. This is a very small language model. Similarly, whenever you Google starts suggesting you these things. This is language modeling. So you already know language modeling in some maybe limited way, but you know it. Okay. So let us start. So the goal of language model is to estimate the probability of a sequence. Okay, so if we have a sequence x1, x2 up to xt, the goal of the language model is to estimate the probability of this sentence. Okay? So for example, I believe everybody knows probability. If you don't know, it's not hard. So we'll do it real quick. Okay, so what is the probability to pick a green ball? 5 divided by the total. Right? Okay, so then what's the big deal about language? Why can we not do the same? So if this is our corpus and we want to compute the probability of this sentence or this sentence, why not just do the counting that like we just did? Count how many times we have seen this sentence in the corpus. So this corpus can be all the books in the world or everything on the internet. You can just go compute, or maybe everybody can. Someone could have done this for us beforehand, and then we just look up the number and divide it by the total number of sentences in the corpus. How does that sound? Good or not, or not good? But we just did it here. Why it doesn't work with the language?
Could be because of grammatical issues or connotation issues. Maybe it may count a certain amount of words, but may not convey the emotion that someone's trying to convey with a sentence.
That's good one.
Order is important.
Yeah, I mean, we are not talking about order. I just said, so for example, if you want to compute the probability for this sentence, we will go to this corpus, count the number of times we have seen this sentence and divide it by the total sentences in the corpus that we did here. Green balls. We counted green balls, divided by the total. There we go. So we want to compute the probability of a sentence. We count how many times we have seen this sentence in the corpus divided by the total sentences. So it might not work. Why? Whenever you will try to get creative, sorry. Right?
Overhead involved in this. How much overhead involved in calculating this probability?
Here, I'll give you the answer you want, which is, you're probably not even going to find that sentence.
Of course.
You need to break it down to a different level.
Yes. Right? So whenever you will try to get creative, the probability will be 0. Okay, because no one will have said the same sentence, especially if you start writing longer and longer sentences, nobody has written that exact sentence. Okay? So the probability will become 0. Whenever you will try to get creative, the probability will become 0. Okay? Because nobody has written that sentence before. Of course, it will take a lot of time as well. Okay? Okay. So for example, for both of these sentences, the probability is 0. But you might be wondering that the first sentence is more likely than the second one. Right? Because the last one is the ordering is not proper. Right? So, but the probability is 0. So probability 0 is not good, but smoothing, we have been smoothing all the way. So we could have done smoothing, but smoothing will still not solve our problem because the first sentence is more probable or more likely than the second one. So what we should do? What we always do. The problem is difficult, we try to break it down into smaller chunks and then solve smaller chunks. Okay? So what we can do is, we can go back to probability. There will not be a lot of math, I promise, just a little bit in the beginning, just to set our basis right. Okay? So to compute the probability of this sequence, how about we start computing the probability of one token or one word given all previous tokens. Okay, so if we can do that, in that we can just multiply all the probabilities, and here we go. Okay, so now the computation is easy. We will not need to find that exact sentence in the corpus because we can do it for every individual word. Okay, and we can still run into that 0 issues, 0 by corpus size. We can overcome that with smoothing. Okay? So let us see a quick example here. For example, if we just have 4 words, probability of I saw a cat. We want to compute the probability for this token. What we can do is, we can compute the probability of I, because there is nothing before that, so the conditional will be gone. And then we can compute the probability of sa. This is an animation, so it will keep running. Let us follow it now. Probability of sa given I, multiply these two. Then probability of I given I saw. Then probability of cat given I saw a. We compute all these 4 numbers, and then we get the probability of this sequence. Okay? So this is pretty much language modeling. We want to compute the probability of sequences. Okay. So if we can do that, so what's the big deal? I mean, who cares about these probabilities? Does anybody care? No. So I mean, what are we doing here today? Okay, so what are we doing here today is, if we have that technology that we can compute the probability of sequences, the great thing we can do with that is we can actually generate language. Okay? So if we have a good language model that can give us these probabilities in a reasonable fashion, we can generate language at its own, without any supervision, blah, 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 at its own. If we have a good language model, what we can do is we can just randomly sample a token given previous tokens. Okay? If we can generate one token, what does that mean? We can generate another one, another one, another one. And if the language model is good enough, like we have these days, they were not that great back in the old days, but here today we have those models. By just sampling tokens one at a time, we can generate really coherent language. Okay? So, and theoretically speaking, just doing this should be sufficient to generate meaningful dialogue. Okay? Although ChatGPT could not do it, it needed supervision. Okay? But theoretically, we should be able to do that without any form of supervision. Okay? Okay, so now you like the idea of language modeling, that computing probabilities is actually very, very helpful idea. Okay? Okay, so let us see how we will generate that. So we will need to start with something. It can be just S or whatever. So let us start with I. Oh, we are already down the road. So if we already have generated was, we can compute the probability of all the words in the English dictionary given I was, and then compute the probability. Let us wait to finish it, and then we will start again. Alright. Maybe I can just, yes. I, probability of all these given I, and then either we can just select the token with a maximum probability, that will be known as greedy, or we could just sample. I mean, there are so many strategies to generate. Okay? Keep it doing, and we will have language generated. Okay? And the promise is that if our language model is good, it will look coherent text. Okay? Okay, so now we just have to answer one question and we should be good to go. The question is how we will compute those numbers, the probabilities that we just saw here. When we have I, we want to compute the probabilities of all the words given I. Okay? So we just need to know these numbers. Where will these numbers come from? What happened to my animation? Did it work? No. Okay. So, but I remember you saw probability of all the words given I. Those small probabilities. Where will those numbers come from? So we can just take a corpus, maybe download some data from internet or download Wikipedia and compute all these numbers. For example, if we have a sentence, we want to compute the probability of learning given deep. We can compute the numbers of this and the number of this, and there we go, simple math. Okay? So now let us go back to the history, see the first language model, and then we will cover maybe a few other very key ideas that we have seen so far. Okay, so the first idea is n-graphs. Okay, so if we want to compute the probability of this sequence, x1, x2, x3, x4, so using that conditionals, what we can do is, we can compute the probability of x1, and then x2 given x1, x3 given x1, x2, x4 given x1, x2, x3. Okay, so you see where this thing is headed. If we had a very, very long sequence, so the last probability will have everything until t minus 1. And that token will have very, very low probability, because we will not have seen that token as well. Okay? So, is it possible that we don't condition on everything we have seen in the sentence? So, for example, if we want to compute the same probability, we keep going, but we just condition on the last two tokens, not on everything, just last 2 tokens. So here we're already 2, so we don't care. So to compute the probability of x4, we just consider x2 and x3. We don't care about x1. Can we do that? Or to compute the probability, we just consider the last token. That's it, nothing else. To compute the probability of x3, we just consider x2. Or to compute the probability of x4, we just consider x3. Or you can go even to the extreme level. We just compute the probabilities of the tokens. That's it. We don't condition on anything. Is it possible to do or not?
Very cheap, do it all the time.
It is very cheap, but mathematically we should be able to do that. Otherwise, these probabilities will not be correct, and whatever we do using these will be wrong, right? So mathematically it's possible, right? So the idea is coming from the Markov chain. So in simplest word, what these Markov chains say is that present is independent of past given recent past. Okay, so the definition of recent past depends on us, what we want to do. So we want to condition on nothing. We don't consider the past at all. We just consider 1 token. We could just consider 2 tokens. We just consider 3 tokens. Okay? So this thing will be known as a Markov property of first order, second order, third order. Okay? And in the language modeling, these things are known as bigrams, trigrams, 4 grams, 5 grams, 6 grams. I mean, that's why we have the name n-grams. Decide on something and move on. Okay? Alright, so using this n-gram technology, we can actually generate, compute these probabilities, and if we can compute these probabilities, we can generate text. Okay? And this is pretty old idea. Okay? Any random vague ideas, how old it will be? A year.
1950s.
50s. So I can give you a guess. So these Markov chains are from early 20th century, 1905 or something like that. So this idea must have come after that. This is just an example if you want to go over. Yes, so pretty close. 48.
Well, the Bell Labs and grant work.
Yes. Right, so this is a paper. I did some digging and I was able to find the paper as well. Okay, so essentially this is the first n-gram language model, pretty old. Okay, and using this technology, we were not able to generate great language, but we were able to generate some text. Okay? Alright, so moving on, you might have imagined some limitations with this. What are the limitations? A lot of limitations, but the most important one is inability to capture long-range dependencies. Because we are only depending on the last few tokens, depending on the size of the n, we will not know what was said 10 tokens away if we are using 4 grams, right? So we will not capture long context. Okay? And of course there are other issues as well, sparsity, difficulty to capture handling out of vocabulary tokens, blah blah blah. Essentially this is the main hurdle. Long range dependencies. Okay, so that takes us to the next big idea in the history of language modeling. That is known as recurrent redundancy. Okay? So if you recall, with the n-gram, we were actually trying to predict this probability. Probability of token xt given only previous n tokens. Okay, so with that we ran into the issue, it doesn't capture long range dependencies. And if we increase the size of n, this will increase exponentially and we will not be able to go beyond 6 or 7. Google used to have these data sets, 5 gram, 4 gram frequencies, and you could just look up the numbers and move on. Okay, but even they could not have like 20 gram or something like that. Okay, so with this recurrent neural networks, what we can actually do is we can condition our XT on everything. Okay, and essentially what we will try to do is we will try to capture this whole sequence in the form of this hidden state. Okay, and if we can get this approximation reasonably well, we will be good to go. Okay, so what is this HT? You can think of HT as maybe multi-layer perceptron, W transpose X plus B, and some non-linearity there. Okay, or it can be 1 layer, 2 layer. I mean, many variations exist. The simplest variation is it is just a linear operation with some non-linearity added. Okay. So how to compute that is it can take in current token and previous hidden state, and it will give us new hidden state. And we can keep doing it recursively. So for example, if we are here, we will use this previous hidden state and current input, concatenate these two, pass it through this MLP, multi-layer perceptron, and it will output new hidden state. And if we also want to generate a token, this can be another linear layer that will give us a probability distribution over the vocabulary, and we can select a token. So that token can be passed here. Okay. So this recurrent neural network. So there were several advancements on this because it had some issues. For example, you might have heard the name of LSTM, long short-term memory, and then this became too complex, and people tried to simplify it as well, named as gated recurrent units, GRUs. So essentially the idea is recurrent. We should be able to capture long-range dependencies by capturing everything, whatever has been said so far in this HT. Okay? Alright, so let us quickly see how we can train these models, and then we will try to move on. Okay? So if we have the input, I saw a cat on a blah blah blah. Okay? So we will just take the input, and at every time step we will try to predict the next token. Right shift the inputs. Okay? So when we are inputting I, our goal is to predict saw. When we predict saw, our goal is to predict R. Okay? A, cat on. Okay? Alright, so and then these are recurrent RNN, any form of RNN. It can be LSTM, can be GRU, or vanilla RNN, etc. So these connections show that, so you can think of this as HT, previous hidden state. So this model does not only get the embedding of A, it also gets what has been said so far. And then it tries to predict cat. Okay? And it can be 1 layer, it can be 2 layers, it can be bidirectional, a lot of ideas are there. But the key idea is this recurrence. What has been said so far. Okay? And how we do that is we initialize our RNN, okay, try to predict I. So whatever the probability of I is, we try to maximize that and minimize all the other probabilities. And how we do that, we can use that negative log likelihood, or more famously known as cross entropy loss. Okay? We compute the probability, so essentially this is the target. We increase that probability using this. We minimize this loss, negative loss. Okay? So if we have a good model that is trained using the RNNs and that entropy laws. With that, we can actually generate language now. Okay, we can pass in tokens one at a time and get this distribution and maybe get token with the highest probability with greedy decoding, or we can just sample, or top K, top P. I mean, a lot of possibilities are also there on the generation end. We can generate language. Okay, so essentially, this is embedding. These are our RNNs. So we got this H hidden state, and then we just have this linear layer at the end. And if we run these are usually known as logics. If we run the logics through a softmax, we get a nice probability distribution, and we can just sample one token from there. Okay, and these ideas are also very bold. Okay, so these are not explicitly for language, but it could model sequence data. Okay, the first use of RNN is also pretty old, from 1990. Okay, and then this person, Joshua Bengio, I believe everybody will know that person. He actually really made RNNs popular with when he started using RNNs with deep neural networks. Okay, and yes, so essentially this was maybe not the first, but maybe the first decent language model that could generate some form of language. Okay, and when 2003. Okay, so far so good. Everybody is with me. Nobody is sleeping. It looks like. Okay, so and that takes us to what was the bad, or what were the major issues with this architecture. So the first issue is what it was supposed to solve. It could not capture long-term dependency. Any ideas? I mean, that was the purpose of this RNN. That was the purpose of RNN, to capture long-term dependencies, and it could not. So you might, you can imagine why it could not, or not. Let's go a little bit back and just try to show you something. Yes, here. So for example, you see this hidden state is supposed to capture everything that has been said so far. And usually this is a fixed length vector. Okay? So you might imagine that if the size is 300 dimension, 400, whatever, it cannot capture what was said. 15 words past, or 100 words, or maybe if it was a long book, this fixed length vector cannot capture everything. Okay? So essentially, in fact, Joshua Bengio was the first person who pointed out this limitation. Okay? And they did some empirical work, and they showed that RNNs can capture up to length 15 really well. But if we start going beyond that, so they showed plots, and the performance was really, really bad if we go beyond 60 words. Okay? So essentially the performance was dropping, like, okay, it's 15 token, and after that the plot was like this. And very, very bad, because of the limitation of the fixed length factor. Okay? And the other issue was related to compute. RNNs, because every subsequent token will need that previous token has been processed. We cannot run any parallel things, or we will need to process one token at a time. Right? If you go back once more, here, yes. To compute this, we need that this should have been computed. Right? We cannot run anything in parallel. Okay? So, all right. So that takes us to GPT of chat, not in fact GPT, it takes us to transformers. Okay, so this was the main idea after a long time, transformers. The main paper was attention is all you need, and it has not been long that this paper was out, but it has changed everything. At least in NLP, it has changed everything. Now we do things very, very differently than we used to do. Okay? So what is this transformer? So this is the original architecture you might already have seen. We will try to go into this, not this side, but this side. So essentially, this is encoder side, this is decoder side. This thing is known as attention block or transformer block. And they said, okay, you can have n of these blocks. Okay, and what is inside each block is multi-head attention, some normalizations, then some MLPs, multi-layer perceptrons, and then some normalization once more, and then some residual connections you also see here. Okay, the decoder is pretty similar with just one difference. Instead of this multi-head attention, we have masked multi-head attention. Okay, so using this idea, different kind of architectures came into being. So this is the original architecture, right? We have encoder, we have decoder. So in the encoder, everything can see everything, okay? But in the decoder, we can only see in the past. Okay? So, and a lot of models are actually using this architecture. One of the well-known model is T5. You might have heard the name, T5 from Google. Okay? So this is encoder stack. Essentially, whenever we are computing the embedding for any token, we see everything. Okay? And then, essentially, this is the idea where we are interested in. And so far, it seems like this is the winner idea. This is pretty old idea from NLP. Given the past, we should be able to predict the future, right? So essentially, what we try to do is, whenever we are here, we try to predict like. We input like, we try to predict this. Like condition on the past. Okay? So this is known as decoder, or the more famously known as GPT model, the decoder series. This is, by the way, encoder, and BERT is the most popular model in this series. Okay? So we will not talk about these. If anybody is interested, we can talk offline. We will talk about this idea. Okay? But I mean, essentially everything is pretty similar to one another with just small variations. Okay, so GPT comes in different sizes. I mean, deeper, wider, different sizes exist. For example, small, it has the dimension of 768 and only 12 blocks, and you have deeper and wider models, if you see at these numbers. 12, 14, 36, 48, and this is the architecture of GPT-2. GPT-3 was even deeper, even wider, and even deeper. Okay. All right. So the key idea is we input R, we try to predict robot. We input robot, we try to predict may. We try to input may. We try to predict not. Given the previous tokens, we try to predict the next token, next token, next token. Keep on doing, like the language modeling we have learned so far. Okay? Alright. And one major difference between this attention and this attention, masked attention. So this self-attention, whenever we are trying to predict, get the embedding for this token, we see on both sides. Okay? Whereas in a masked attention, we just see in the past. Just previous token. Okay? So this is more suitable for generation. Right? Because whenever we are generating something, we will not know the future. We will just know the past. Okay? So that's why we only want to pay attention on the previous tokens. Okay? Alright. So this is essentially what we do. For example, if we were here, we were trying to predict the embeddings of obey. we will consider all the previous tokens and compute its embedding, and at the end we will have a linear layer to make prediction. Okay? And since there are multiple decoders, the things move forward like this. From this decoder to the next, to the next, to the next, and in the end we make a prediction, and then we input that token and we try to predict the next token. Okay? So the good thing with this is these things can run in parallel. Okay? So one major difference between RN and N transformer was the embedding for every token can be computed irrespective of the previous embedding, because we don't rely on anything being computed. Okay? We can just consider all the previous and remove the future one. Okay? And it's pretty easy to do. Alright, so let us start going a little bit inside, and depending on the time, let us see how deep we can go. Okay, so this is, I have just, what happened to this? Okay, yes, so this is the decoder side architecture. So this slide, so essentially we are here. Okay, we will try to go inside and all the way up, inside each of these layers. Okay, okay. So this is the first embedding. So how we get embedding? You can think of embedding as a big matrix, and what are the dimensions of this matrix are, we have this embedding size and this is our vocabulary size. Okay? So this GPT and all these, yeah, not all, most of these models have this size vocabulary, 50,000 something. Okay? So whenever we see a token, we can just do a lookup, or if we get one hot encoding of that token and multiply it with this matrix, we will be able to get that specific row. Okay? And the second thing is we don't know the order. So one word, what is its position in the sequence? Okay? How we can do that? We can just get a positional encode. Okay? So the positional encoding is also very similar. We have this embedding size and we have this context size. This context size also depends on the model, the version of the model. Okay, so mainly we are talking about GPT-2. GPT-2 medium is the default one. That has a context size of 1024. Okay, so if we know the position, we will just be able to look up, or again, if we have one hot encoding, we can do that matrix vector multiplication, and we will select that row. Okay. The next thing we do is, this is our token embedding, this is our position embedding. We add these two, and this is known as, you can call it H0, the hidden vector at, because it has not been passed to the actual model yet. We are somewhere here. Okay. All right. So let us go inside now. Inside we have masked self-attention, and then feed forward, and then we have several of these blocks. Okay. And intuitively, without going into the details, what happens inside, what usually happens is, for example, if we are at this token, in the masked self-attention, we try to compute that, to compute the embedding for the word it, how much attention should I pay to the previous tokens? Okay. So for example, if you look at this example, these are not real numbers, just made up numbers. To compute the embedding of it, we need to pay 50% attention to robot, because most probably it is pointing to robot. Okay. Alright. So once we get this, we pass through to MLPs, and then we keep moving forward. Okay? And then once we have, once our input has passed through all the decoders, how we make predictions is, we have this token embedding, very similar to the one we had in the beginning. Okay? Some architectures share these weights, but mostly don't. Okay? So this is our final output. We multiply it with this, and we get usually known as logits. We can sample from here or we can take the word with the highest probability. We got one token. We can keep on doing the generation. Okay. This multiplication, this logic. Some people try to run softmax to get a nice probability distribution. If you like, you can also do that. And then we can sample or use greedy decoding. Okay. All right. So far so good. Now we are trying to go inside this block. Okay, self-attention, or known as query, key, and value. Okay. So intuitively you can think of, this is my query, it. To compute the embedding for it, what I need to see is, you can think of these are keys, keys meaning labels on the file cabinets. Okay. So essentially this operation, mathematically you can say dot product followed by a softmax. Okay, so this is my query. I will take dot product of this query with everything and then run a softmax. So softmax will give me a nice probability distribution. So essentially this nice distribution will tell me that to compute it, I should pay 50% attention here, 30% here, and something there as well. Okay, so these are the scores we got by taking the dot product of query and keys and running through softmax. The last thing is value. What is value? You can think of value as what is inside the file. Okay. So this is a probability distribution. If we multiply these two, what we will get? We will get something like this. So if the number is higher, take 50% of this. If the number is very, very small, take maybe nothing out of this and then sum these up. This is the embedding for our this token. UKY. This is the operation that we do. Okay, the first operation in this. Okay, I simplified it a little bit. There happens a few more stuff as well. Okay, so let us see UKY. So essentially all these layers, these Q, K, V, they have corresponding weights. Okay, they have their own weight vectors, weight matrices. Sorry. Okay, so this is my query. We perform this dot operation and we get this. Okay, so far so good. And then we can run softmax over these keys and we get these percentages. Okay, percentages meaning that how important is this word. Okay, and then the last operation is we multiply with the values. Whatever, so these numbers, 20%, 10%, so these numbers that we are here now, okay, we multiply it, okay, we get these vectors, we sum this up, we get the embedding for this token. Okay, so you might be wondering that we were not supposed to see in the future. Why we are seeing in the future? Because we are computing the embedding, let's say for x1, we are seeing in the future, right? So this is not actually masked self-attention, this is self-attention. And now we can easily see how we will mask it. Okay? So the idea for masking is very easy. So once we are computing the embedding for this, we can just set these key vectors to something very, very, very small. Depending on the implementation, we can just set it to the smoothing value. The smoothing, it's usually very, very small, 10 to minus 37 or something, depending on the CFP, right? So something very small, or minus infinity. Okay. So what will be the effect? So let us quickly see. These numbers are not real. Okay, just made up so that you can make sense what is happening inside. Okay. So yes. So once we input robot, our label is must. Next token. Okay. Once we input must, our label is obey. When we input obey, our label is orders. Okay. So these are our queries. These are our keys. We take the dot product and then so these are raw scores before softmax. Okay. Next we apply softmax. Okay. So once that number will be these numbers, the future numbers, we should make them very, very small, and this is these are how our scores will look like. Okay? So now the last operation. Last operation is masking. So these maskings, once we will run these things through softmax, these numbers will become 0. Okay? So to compute the embedding of the first token, we should pay all the attention to this token because we don't have anything in the past. Okay? So to compute the embedding of the second token, we should pay 52% attention to the current and 48% to the previous. This is how we get contextual embeddings. Okay? So this is pretty much that happens here. I have just skipped one thing that is known as this multi. Okay? I will just quickly walk you through what is the meaning of this multi. Okay, so the meaning of this multi is we usually have multi heads. Okay, to run these things in parallel. Okay, just imagine we had 3 heads. Okay, so if this thing was our one vector, we will just split this vector into 3 different heads. So one positive side effect of this is that we can run things in parallel now. Okay, we don't because each head is operating at a specific part of the vector. We can speed the things up, and the other effect is that different heads capture different things. Some head will capture short-term dependencies. Some heads will capture long-term dependencies. Okay. So yeah, I mean essentially this is query, this is key, this is value. So this was the original. If we had 3 heads, this is my query 1. If it's Q9, the first part of Q9, the second part of Q9, the third part of Q9. If we had 12 heads and our original head was 768, instead of 768, we will get 12 into 64, depending on the heads. Okay, and now we operate on this. These are my queries, these are my keys, these are my values. And we perform the same operation that we just discussed, just slightly different way. Okay? So far so good. I will need to rush a little bit. Okay, so just stay with me. Okay, so this is the thing we just talked about. Layer norm. I think all these frameworks just provide layer, just normalization, so that our values don't overshoot or don't get zeros. Normalization. Okay. And then I will talk about this feed forward. So feed forward is a pretty standard operation, W transpose X plus B. Okay. So essentially this feed forward has 2 layers. Okay. The first operation is we open up. Okay. So we had this 768. So we project this 768 vector to 768 into 4. Just try to expand it. Okay, it will have more space to express itself. Okay, and then in the second layer, we try to get back our 768. We try to open it up here and then, try to open up here and then try to get our original size back. And the last output will be given to our linear layer that will output upward. Okay. So not much time left, but we will try to quickly talk about ChatGPT. Okay, so this ChatGPT, because they did not write any paper, so not a lot of stuff is out how it operates, but the key ideas are here. Okay, so what they did was, so they already had this ChatGPT 3.5, GPT 3.5. Okay, pre-trained on huge amount of text, exactly the way we saw. Okay. So theoretically, I said that we could generate language using this technology, but people somehow don't like this language, even this ChatGPT 3.5. Okay, so to make it so that people like it, what they did was this. Okay, so they created a prompt meaning a prefix. Okay, and then they hired a lot of people and ask them, okay, how we should complete this text. Okay, so the labeler demonstrates the desired output behavior. Okay, so if we, let's say, this thing can be a question, explain reinforcement learning to a 6-year-old. It can be anything, but the kind of questions we ask ChatGPT these days, and then they hired like a lot of people, okay, and ask them to generate what it should say next, okay, and then they train the model in the supervised setting, okay. So once we have this model is expected to generate text that, or generate responses that humans will like, okay. So to make it even better, what they did, they brought in another algorithm known as reinforcement learning with human preferences. This is very popular these days. So what they did, they took this model, this fine-tuned model, okay, give it a prompt, generate 4 responses, and hire more human beings to rank the responses. What is the best response? What is the worst response? Right? So if we have ranking, then we can actually learn a reward model. Reward model meaning given 2 responses, what is the response human likes more? Okay. So if we have this model and this reward model, we don't need humans anymore. Okay. What they did was they used this algorithm known as PPO. We don't have time to go into the details of that. So essentially what they do is they give the prompt to the model. Okay. So this model is initialized with this model actually. These are the same models. Okay. So give the prompt to this model generates an output, this reward model gives a reward, and this model optimizes itself so that it generates the responses humans will like, humans will prefer over other responses. Okay? And yes, some works we have done, this is one of our work was on personalizing task-based dialogue systems. This idea is pretty similar to ChatGPT. The difference here is instead of the reward function they had a lot of people actually to do this labeling. We did it without that many human beings. Okay, and another difference is that our paper came out earlier than that. Okay, so this ChatGPT came out maybe November, December. So this paper was accepted in CIKF 2022 last year. We presented, luckily, we presented before that. Otherwise, it would have been hard to get this paper out. Okay, and then there's another work we just recently did. Actually, Alif did, one of my PhD students. So zero-shot generalizable task-oriented dialogue systems. So we train the model to do something, and we expect it to perform on new unseen tasks. For example, we train on restaurant ticket booking, and we expect it to work in the hotel room booking, something like that. Okay, and then another work, it also got recently accepted at WWW. Here, we actually joined 2 different models. Okay, one is weakly supervised, another is a zero-shot learning model, and then we combine labels from both models. One model generates labels for the other, and this model generates labels for the first one, and they are iteratively trained. Essentially, this model was BERT. Okay, and another work that we recently did. Another student of mine, Mughis, did it, and from the reviews, from user reviews on Google Play, we were able to predict key issues. That this review doesn't say anything meaningful. You know, there are reviews that just abuse you or just praise you for nothing, right? So those are not essentially very helpful for us to improve, or for developers to do something. So using this work, we use contrastive learning. So for example, worst app ever. You see, this is not really helpful. I mean, what we can do about this worst app ever? Not very meaningful, right? Whereas if we have something like click on this and it does this, this is very meaningful review, right? Developer can actually take this review and improve the app based on that. So using this work, we were able to predict this kind of reviews that are actually informative. Okay? And I think we still have some time for questions. Yes. Not much, 5 minutes. All right.
All right. Any questions? When you say your question, make sure you speak, loud enough so that.
I will try to repeat. Yes.
So why are most large language models decoder only rather than encoder-decoder architecture?
This is a very interesting question. So one simple idea is you could see that if we have encoder and decoder as well, and if we just have decoder, half the parameters are gone. So we could build bigger models with the same number of parameters. Okay, and this decoder model have actually been super successful with natural language generation. Right? In the generation, we are not supposed to see in the future. So that's where they have seen the most popularity. Okay? But the idea is generation, because generation is so generic, we could formulate any task into a generation task. Right? For example, we can do classification with generation, but we cannot do the other way around. Right? So essentially what people are doing these days is, they say, okay, this is good for generation, so let us formulate our problem into the task of generation.
Questions?
So many years ago, I actually did a lot of stuff with n-gram analysis, working with some anthropological linguists, basically doing tools for etymology. And that certainly was a very rich thing and worked very well. But the interesting thing is, rather than thinking of n-grams as being used to generate, it was basically used to create a consistent model of what was going on, sort of behind the scenes. And to put it very bluntly, I more recently used that. About a dozen years ago, I had a PhD student who did compiler analysis of performance expected at runtime in terms of power consumption for individual instruction sequences looking up to 1 billion instructions ahead by doing variable precision n-gram analysis to basically build up these systems of equations for which we could actually take power measurements and predict power at the instruction level. So what I'm getting at is, everyone keeps being very excited about generating phrases here and things like that, but is there stuff that you can use to play this backwards, so to speak, to get some of the underlying properties? For example, using this kind of analysis, do you think we would be able to do something like predicting the power consumption for instruction sequences in a better way?
So, yeah, I'm not maybe an expert in that field, but I mean, this is what is happening right now. Maybe not exactly what you said, but people are building now compilers based on these ideas. And
well, this is playing it the other way around. This is saying, given a sequence of instructions, be able to, for example, predict what the power consumption is for that sequence. Which sounds simple, but there's so many complicated things going on in machines today that that's actually extremely difficult to do. But as I say, n-gram analysis actually gets a good handle on that.
yeah, I don't know about the power consumption, so maybe I'm not the best one. But essentially, because that's why I took the ideas in sequence. So these powerful language models, they still capture n-gram. So the idea still goes back to n-gram. In fact, the first few layers, they are capturing n-gram. I mean, precisely they are capturing n-gram. Right?
Right. So think of it this way: if you had a sentence that was just given to you, would you be able to say something about probabilistically, what the likelihood was of that sentence occurring?
Yes.
Okay. So
This is
what
language models are supposed to do. Yes.
right. So basically, that should be able to be applied in other fields to do this kind of analysis. We can talk more about that.
Yeah, I mean, as I mentioned, a lot of things are happening actually around these ideas. The applications of these models in like a range of fields, right? So, I mean, because the ideas came from NLP. So NLP people are of course using for NLP, but there are like a lot of people are doing. For example, this model has been used to generate music. Right? So that was like the most fascinating for me so far. But this power consumption might be even more. I mean, I just don't know the details. But say, yeah, as soon as we have a sequence, here we go. Use this technology. Yes.
Sorry, I know we're out of time, Professor, but I was just curious from a pros and cons standpoint, simply saying, if you have a machine learning package like from a robotics standpoint, you have a friend going back to college on electrical engineering, so if you train, for example, like an Arduino Mega, like on a weekly trained task, I'm just guessing based off what you were loosely saying, that like could that replace certain essential workers? Like, okay, now this robot has been trained with a rudimentary task, and then it stops these shelves, and like policy runs out. I think I googled it before 5 years, and so then technically speaking, that Arduino Mega could be like a monorail going down and stacking accordingly. Is that true that it could be trained with machine learning packages that replace certain individuals?
It is already happening.
No, I know,
You
but
have-
like to a larger extent.
Yeah, so if I get correctly, the question is that can these models replace some jobs?
Well, I mean, to a larger extent, like, I've only heard some stuff on YouTube, and a friend of mine said, like, wouldn't it also eliminate or stifle certain artistic capability, because it can also mimic other artists or, like, even their work? So wouldn't that limit certain, like, actions or?
I mean, my view on this is very different. I mean, this has been happening to us, right? I mean, in our lives, maybe not here, but internet was not there. I was very young at that time, but internet was not there. Internet came, a lot of people reinvented themselves. So maybe we will need to reinvent ourselves. Right? I mean, mobile, I mean, now we have like 20 different devices in our pocket, right? So we reinvented ourselves. So that's how humans have survived through the history.
So, what is the purpose of having so many splits of decoders in the GPU? Like, I mean, obviously the performance will improve, I get that. But what is going on as we pass through each of the decoder layers?
Yes, so it's not well explored direction, but essentially as of now, what we know is the first few layers capture n-grams, okay, and as we go higher in the layers, they capture semantic meaning. Okay, and these MLPs, they are memories. They store information. They store facts, whatever they have learned from the text. Okay, so yeah, not exactly the brain, but kind of.
Maybe the context,
Yes.
like from granular level to more.
Yes, so different layers capture different things. The first few layers are at the n-gram, like the word levels. This word after this word, and higher essentially capture the semantic meaning. Right? In the n-grams, we cannot replace good with another synonym of good, but in the last few layers, they can just replace one word with another just seamlessly. Yes.
So some people are criticizing about this generative models. Like some famous people who say these generative models are doomed.
Yes, Ian Lagun.
Make up stuff, errors propagate exponentially. I'm just curious, what's your opinion about this?
So, I mean, this is not the perfect technology, right? So, you can imagine if you train something just on raw text, it will not be perfect, right? But it has the potential, and people are working on that. For example, I mean, there are many issues with these language models. For example, they hallucinate facts, which is not good, but, I mean, so...
They very credibly hallucinate facts.
Yes.
That's even worse.
Right, so then people are working on these, right? So hopefully we will overcome these issues. I mean, as an architecture, some people oppose to that as well. For example, Ian LeCun, you might know, he is like a great opponent. I think you used his frame, are doomed. So, I mean, I don't agree with that, right? So there are limitations. So people will come up with limitations, or maybe, so you see, you have seen in the history, there is a limitation, we try to overcome. Sometimes we overcome, sometimes we come up with new architectures. So some people are trying to come up with new architectures that can overcome these limitations. Right?
All right, our time is up. If you have questions, you can ask the speaker, when you enjoy the piece. Okay. Don't forget to sign your name, please.
Okay, thank you for all the